Alright, how's it going, everyone? Welcome back, and we're going to be working more on the lightsaber again. This is a huge project, so still a ton of work to be done. We probably even barely scratched the surface, but last time we finished the schematic, and so this time we need to go through and kind of review a lot of things and see what changes we can make it better, because we hit all of the basic requirements, but since we probably have a little bit of extra IO, and now that we understand better how the whole circuit looks, we can go through and make some changes to kind of better optimize the entire system. So that's going to be the goal for today. As usual, we have Dogecoin bounties, so if you want some Dogecoin, try and claim one of these bounties before someone else does. And let's get started. I'll turn that music back on. I totally made it like halfway through the last stream before I remembered to do that, so try to make a point to do that immediately here. But if you stop by, also say hi or whatever, give me something to chat about. I don't mind chatting while I'm working. Okay, so probably the biggest concern of this entire project is going to be this power supply circuit. This whole thing is ridiculous, and for good reason, obviously. And I can't wait to see how it all works. But we need to make sure to make it pretty robust, because what we're trying to do here is pretty extensive. It's pretty ambitious. It's not as simple as just powering something from a battery, but we're trying to use rechargeables and lithium ions, and we're trying to use an 8.4 volt system and drive a lot of current for a long amount of time. So driving 4 amps from rechargeable batteries is a lot. So yeah, we'll see. All right, I guess first things first then. One thing I wanted to check is what would happen when the system drained. Like when the voltage just dropped. And so I want to check out this regulator, because I'm pretty sure it has some shutdown modes or something if it detects a power drop. So I want to see what happens in that scenario. So that being said, we need to look up this exact part. Regulator IC, resistor, it's going to be one of these U parts. 2-cell SOIC charge. This regulator right here. Okay. Want to find it on their actual website. But hang on, my internet's going to be slow too, so that's always a thing. All right. We are using the 29501-5.0. And we know that ours has a flag pin. I imagine if there's a fault, something gets thrown there. 501, here it is, the flag in enable. Enable will always be held a certain way. So let's see what we got here. It's not adjustable. All right, so our output voltage Load regulation, dropout voltage. 501. Okay. Okay, so this is when, yeah, so typically around 370. I'd love to see a graph for this, that dropout. Man, you could buy a version of this that has a 15 amp output. Jeez. That's intense. Okay. I want to understand how, I think if I look up how the flag pin works, I can probably see what's going on there. Active low error flag, output signal that indicates an output fault condition. Okay. Oh, interesting. They have minimum loads too. You have to load them at least 10 milliamps or it won't be in the expected range. The regulator is necessary, yada yada. Error flag, which looks at the output voltage and signals an air conditioner when this voltage drops 5% below its expected value. The error flag is an open collector output that pulls low under fault conditions. It may sink 10 milliamps. Low output voltage signifies a number of possible problems, including an overcurrent fault and low input voltage. That's probably what we want. So the flag output is inoperative during overtemperature shutdown conditions. Interesting. Okay. So allows on-off control of the device. Special design allows zero current drain when the device is disabled. Only microamperes of leakage current flows. The enable input has TTL CMOS compatible thresholds for similar logic, or maybe directly tied to something under 30 volts. Enabling the regulator requires approximately 20 microamps of current. Okay. So I'm trying to figure out a way, like, one of the things I'm concerned about is over discharging. So the lithium ions only go down so far, right? Each cell can go drop down to 3 volts, I believe. And I'm afraid of pushing those, like having some sort of leakage current that continues to discharge those to the point where they're unusable. So let's see what I can come up with here. Let me find the battery. I can find the spec. Adafruit 1781. All right, here we go. Included protection circuitry keeps the battery voltage from going too high or low, which means the battery will cut out when completely dead at 2.5 volts. However, even with this protection, it's very important that you only recharge them at a rate of 0.5 C or 1 amp or less. Have thermistors built in. This is why we suggest charging at half C or less. Of course, you can charge at a lower rate. It'll just take longer to fill up. Okay, so this is good, actually. If they have built-in circuitry that basically kills these things when they reach too low of a current, then I think we're okay. Yeah, all right. That's interesting. I didn't realize that they had that. So that could save us a lot here. I'd be curious to know how that circuit works. I don't know if I think it would be in here, but volts with 0.2. I like all these tests that they do too. I remember when Samsung was blowing up phones, they were talking about in their commercials their 9-point safety test or something that they were doing to every battery. Probably similar to the tests here. Let's see. Yeah, it doesn't really say. All right. But we know that, okay, so knowing that it has dropout protection circuitry, that's awesome. So what do we do from there? I guess then in that case, we don't have to worry too much about them over discharging. Because they'll cut themselves out at that point, which is great. So, okay. Okay, that's something else I never checked about. Batteries in series. Can batteries in series be recharged? I don't actually know the answer to this question. I just kind of assumed you could, but... Okay, yeah, you can. Interesting. Okay. So that's good. So I don't have to worry about cutting off the power or anything. So the last thing is like flow of the power. Obviously, like if we connect them this way, there's going to be kind of a short scenario where, say, like these two batteries in series have a slightly higher voltage than these two coming from the factory or something. Okay, that's just, it comes that way. The power is going to flow out of this one and into this one in a short condition. It will be super fast. Possibly heating up the wires and the batteries, faster than you would want. So should we do something about that? Since we're driving to 5 volts, what we could probably... This gets tricky, but what we could do... we could put diodes on each of the outputs so that they don't actually all connect together, but instead they all connect through the diodes to the 8.4 volt line. And diodes obviously being made such that current only flows one direction, it couldn't possibly backfill, so you wouldn't have that short scenario. The challenge comes when recharging them. You also need that to flow through a diode. So it requires some changes to our circuit here, but We could do it. I don't know if anyone has any thoughts on that. The other option is, once again, we connect them all to a common point and then put a resistor in each one. That would slow down the max current that we could pull from any battery. We could do something so that it's 1 amp. But in order to do that, there has to be a voltage drop. Yeah, that's not a good option. The diode is much better, definitely. Okay. Let's see, charging batteries. Let's see. Apparently there's like some thought on this because people are like recharging, like car batteries and such. Let's go to this random website that looks like it knows what it's talking about. This is all related to car batteries. I don't know if we can't necessarily take for granted that it's going to count here because those are typically lead acid, I believe. So different type of battery. Hello, you aren't charging. Okay, sorry, I apologize. I'm reading for this. When charging batteries in parallel, you aren't charging the voltage of the batteries, but rather the ampere capacity of the batteries. Changes based on how long the battery is used for 20 hours. It seems like there's no real issue here, except for, like I said, the flow from one side to the other, so we probably should consider that at least. This is that giant resistor, isn't it? 7 ohms. What's going on here? Sense. This is odd. I'm not sure how I feel about this. All right, let's look at charging lithium. Batteries in parallel can be safely charged. All you need to do is follow the safety precautions associated with charging lithium. If you do not know how this works, you can either find someone to do it or you don't try it at all. Most times, using the right tools, the right charger can save you a lot of stress and time. All right, I understand the sentiment, like find someone who knows how to do it or don't do it, but I want to know how to do it, so... Only batteries of the same type, yeah. Okay, it mentioned something about a balancing circuit for series. All right, interesting tips here. Let's go. Okay, electrical engineering stack exchange. Let's just see what the internet's opinion is. Simple packs from the cells out of the same box, having very tight tolerances. This way you can get packs of serially connected cells where the cell will just equal symmetric over the lifetime of the pack without balancing, of course. How to self-discharge the difference in the cells in order not to have significant unbalancing. Your case is much simpler, so I guess you're using low quality cells. The above is only valid for top quality cells. Okay. Interesting. I'm probably going to kill a lot of batteries doing this. Reading about what other problems people are having. All right, let's see what else. All right, let's see what this looks like. Let's see. It's another stack exchange post. 7-volt cells. Placing 3 in series to give you. Flame sprays. Interesting. Okay. Let's see. That didn't really answer like how to do it though. Here we go from DigiKey, a designer's guide to lithium-ion battery charging. Let's see here. Nope. Here's an interesting thing from Adafruit. Let's see. Your project is twice as many as you want to, or you want it to last twice as long. People think, well, I know that if you parallel two batteries, that doubles capacity, so I'll do that. For example, we'll take the parallel. However, you should never do this. Battery can discharge into another, damaging or causing a fire. If you ever need a larger battery, you should upgrade to a larger battery, like this one that is twice the size and has twice the capacity. Batteries are assembled by a company that is experienced and certified to test and assemble battery packs. The individual batteries are tested and sorted by machines so that each pack has matching batteries with the same capacity and internal resistance. Series to get higher voltage. This is also discouraged because the battery won't be able to be charged in a balanced manner. You should purchase a lithium pack that's pre-assembled. What if I want to do this? All right, so evidently my power solution is not fully thought out right now. And that's a shame. Interesting. I wonder what this circuit looks like. I'm going to figure out a way to do this. Oh, man. I probably should have double checked like all of this before I started trying to do it. Let's see. For making this series connections, it is highly recommended to charge lithium batteries. The multi-bank does each other. In some applications, this is not practical, which is why. Okay, interesting. So I probably need to figure out a way to redo the circuit a bit to charge them like they're supposed to be. Oh, this is gonna be hard. The alternative is I have to find batteries that fit my current connectors and things here. Maybe somebody has one? What would it be? It would, what's 3.7 times 2? Because that's what probably the ideal thing is going to be. 7.4. That's what I thought it was. Interesting. I have a few options here. So basically, unless I come up with a way to balance them, it's going to be likely that I do something bad that kills my batteries or sets them on fire or something. There are some options here to at least make this easier to work with, but nothing straightforward. Nothing that's... no solutions for make it easy for me to recharge in circuit. Okay. I'm wondering if I can't create some sort of... Jeez. Neighbors upstairs are so annoyingly loud. I wonder if I can't create some sort of network of diodes, basically, to make sure that this it charges like evenly and whatnot. It seems like a pretty complicated circuit, though. Just trying to visualize it in my head. I could probably keep them balanced if I put a resistor between them. Like, it could probably even be like a big resistor. Diodes on the outputs would keep them from running into each other. And then... how to charge them evenly in series, that's the tricky one. Maybe you could do it with some sort of like voltage divider thing. You would need, once again, diodes going certain ways. And this is going to get super complicated. So how would you do that? Hmm. Just look up charge balancing circuit, see what we get. Oh man, there's like, this gets pretty complicated. It looks like. Eat every pack that we designed. Full charge. No two cells are identical. There are always slight differences in the state of discharge, self-discharge capacity, impedance, temperature characteristics. This is true even if the cells are the... Most typical battery chargers detect full charge by checking whether the voltage of the entire string of cells has reached the voltage. Cells can vary as long as they don't exceed the limits of overall temperature. However, weak cells... Cell balancing techniques. Passive and active. Discharge the cells through a dissipative bypass route. This bypass can either be integrated or external, which is favorable in low-cost system application. The fact that 100% of the excess energy from our cell is dissipated as heat makes the passive method less preferable to use during discharge because of the obvious impact on battery runtime. Active cell balancing is going to be more efficient because of energy transferred to where it is needed instead of being bled off. Of course, the trade-off of this improved efficiency is the need for additional components at a higher cost. Okay, this is a great article, but give me an example. I wonder if there's a chip that like does this kind of stuff. Got some images that I can look through here. I would need a circuit that doesn't require like input from me kind of thing. There's a solution here somewhere. This is one of the biggest things I was worried about in this whole thing, and it looks like I was right to be worried. It looks like there's variations of a circuit that will do this well. Looks like alternatively you could just use ADCs to measure the voltage of every cell and then charge them selectively. Or basically drain current isn't necessary. Interesting, okay. Yeah. Like I said, anyone has any thoughts, I am listening. Because this is tough. I wonder if my charging chip here took this into account. This is the boost. Because it's designed to charge 8.4 volt system, so I wonder if they mentioned it. Let's see. Optional voltage divider for non-standard. Ovation voltage. Interesting. It's like current sensing, temperature fault. Okay. Alright, so it doesn't necessarily look like this is gonna have what I need. But it seems like I do have to do some sort of charge balancing circuit. I'm trying to find something that's not too, I guess, too complicated, like too active. Like I want to just use some passive components like resistors, diodes, you know, and make it work. But I don't know if that's possible. There might be a possibility of getting a part, like a chip that does this. Oh wow, these look complicated. Here's something interesting. Oh, 404 pages. Those are no fun. Okay, here's a part that apparently does something like this that we needed to. Effectively, you throw one of these in line here for each battery. Interesting. So why does this work the way it does? Ground, delay shortened terminal, output of detecting voltage, output type is 5 is the output detecting voltage. So basically, I guess it detects this. Oh, this is some crazy circuit here. Okay, hold on. It's determined. Our voltage monitor IC is for rechargeable lithium-ion polymer using high voltage eyes. Each of these ICs is composed of voltage detectors, reference voltage sources, an oscillator, a counter circuit, and logical circuits. Okay. Yeah, I don't know if this it looks like it's all controlled through something. Okay. There are any other options? Because that was the only thing that looked like it would be easy to work with. Everything else, like, it looks like it exists as a balancer, but I mean, man, it is a hard to use part. A lot of tiny pins and everything. Interesting. I just want to look at one of these, even though I know it's not really usable. Let's see. This better not just be a brochure. Oh, it is just a brochure. Okay. So let's go back to this chip and see if we can figure out what's going on in the circuit here. I think all of their links are broken. We'll look up this other chip too. MM3474. All right, so this other chip that they're listing here is a monitor IC kind of for batteries. There, it took forever to get that 404. Oh, excuse me. It also provides the control terminals of output over discharge detection. Cells connected in series. So is it just a detection circuit for issues, and then just shuts it down if something goes wrong? Like, could you do it without is what I'm trying to figure out. Let's look through this again. Man, I'm going to make no progress tonight because I'm just stuck on this one problem. I was really hoping this wouldn't be an issue, but it might actually be. They're using Zener diodes on everything here too, which is interesting. All right, so what happens if this turns on then? It drains the battery effectively, right? What are the DS pin is not even connected for delay shorten terminal. Start running capacitor C1, C5, stabilize the supply voltage ripple. However, R1 and R5 increase the detection voltage raises due to the through current in the IC. Therefore, we adjust the value to 1K or less. Current is determined. I'm not quite there yet. We're getting close, though. Excuse me. I'm going to figure out a method that makes this work. Obviously, if anyone has any ideas, that would be a huge help right here. Sorry, I just had to look at something. Most of these use ICs to control it in some sort of active method. I wonder if I search like passive charge balancing circuit, if that will give me different results. Effectively, it's all some form of a resistor and then a switch that can be turned on or off as necessary. Here's an interesting and dense paper, which I think a lot of stuff is pulled from. Passive cell balancing of lithium-ion batteries used for automotive applications. Yeah, it looks like passive stuff, even passive stuff, still using that way to control it of some sort. Active balancing does not dissipate energy through a resistor, rather storing the energy from a higher voltage cell in a capacitor and then transferring it to another lower voltage cell. Right. Interesting. Okay. Not useful here, but still interesting. All right. What are some other options? Looks like every scenario here is you have to have some sort of active component monitoring it and then turning switches on and off to charge it. Yeah. All right, reading through another article here. I'll throw it up on screen just because I appreciate those of you sticking with me because this is so boring, I know. For the cell whose voltage is higher than the other cells. So basically, okay, so when you're charging, they effectively turn on and off to keep the voltages even. So they're charging them all together. Okay, that's interesting. This method is not very efficient because electrical energy is dissipated as heat in the resistors, and the circuit also accounts switching losses. Of the drawback is the entire discharge current flows through the MOSFET, which is mostly the discharge current has to be limited to low values, which increases the discharging time. One way to overcome the drawback is to use an external switch to increase the discharge current, shown below. Monitor multiple cells and save time, development, and cost. Most inefficient method of all. Here, only safety and lifetime. Active cell balancing. So what is going on here? The excess charge from one cell is transferred to another cell of low charge to equalize them. It is achieved by utilizing strong like capacitors and inductors. There are many methods to perform active cell balancing. It's commonly used ones. Flying capacitors. I love this solution already just for the name of it. Capacitors to transfer charge from a high voltage cell to a low voltage cell. Once the capacitor is charged, the switch connects it to the lower voltage cell where the charge from the capacitor flows into the cell. Since the charge is shuttling between the cells, this method is called charge level. These capacitors are called the flying capacitors that fly between the low voltage high voltage. I didn't know today's stream was just going to be me reading stuff out loud. And a battery pack. Or buck boost. I like the flying capacitors method. It's interesting. I want to try it just because it looks like it'll be very basic, I guess. Lossless balancing. Oh, basically just measure everything. How does this flying capacitor method work? Like, this doesn't fully explain it. Hold on, I gotta look this up. I just want to see an example. Like, has somebody done this before? Obviously, like, it exists in theory, so... Man, we've reached the point now where we're trying to do something with that's only uses like scholarly articles. There's not anything basic written about it. So yes, I would love to walk through all this math. This is epic. Okay. Somewhere I'm gonna find an example of somebody who's done this. And my fear is that it's done based on a switch that is controlled still by a controller of some sort and not just by like charge levels, I guess. This is for something different. Okay. It's for a booster. Hold on. Okay, I think I might have found something. It's another like scholarly type article, but it might have actually a decent explanation of this. As to the balancing, the capacitor shielding can be categorized into four shielding: the basic switch capacitor, the double-tiered switch capacitor, the single switch capacitor, and the modularized switch capacitor. Cool. Right, I don't need anything like super complicated because it's only 2 batteries. So I honestly just need like the most basic of things. I just don't understand how this works, personally. I don't understand what controls the switch. This actually didn't provide a lot of come on. All these articles are like studies of like the efficiency and stuff. I'm going to find a way. Yeah, so there is a control line controlling the switches and measuring the voltages. Ah, that's disappointing. Okay. So it doesn't seem like there's really a way to do this without having some sort of control. And that could be a serious problem. Oh. My options here, either I have to charge the batteries separately using some sort of charger and then connect them and put some protection in there to keep them from uh, shorting to each other and whatnot. Or, oh man, I have to come up with a method to do this. I could do this with a separate IC, like a different chip, different controller. All right. In the interest of getting something done, there's a lot to think about here, and I need to really think through and research this some. I'm going to look at other parts of this just so we can do something else, because this is definitely a problem we're stuck on. This is taking forever. All right. So let me go over the rest of the circuit, check out other things, and then, yeah, we can look at that later, I guess. So 1, 2, definitely have those 2 IO open. 3 IO left. These switches are debounced. The power button, I'm not as worried about a debounce, but we do have it, I think, on the teensy side. Yep. It has a resistor going to it anyway. And has a capacitor there, yeah. So it is effectively debounced, so that's fine. I wonder if I could do something with comparators on the charge circuit. No, you got to charge the batteries evenly, otherwise the discharge isn't good. You have to keep them at the same level. Alright, well anyways, these can turn on and off pretty fast, PWM. Yeah, that's probably not going to take much change. Honestly, most of this stuff is pretty well worked out. The things that concern me are the stuff that could discharge, but since we aren't worried about that anymore, I'm not worried about turning things on and off. NeoPixels. Oh, that's the pull. That's the signal line, yeah. And then the power, right, goes through. Okay, so that all makes sense. Accelerometers. It wouldn't necessarily be a bad idea to drop some caps for this thing. Although what's internal should be fine, so... Ooh, these have analog inputs. I might be able to use those to measure the battery stuff if I wanted to control it from the teensy. But you can only control when teensy's on, so maybe that's not such a good idea. Motor stuff's pretty straightforward too. Yeah, it seems like the only thing that's seriously in question is this charge thing, so there's not much else I could do other than work on this some more. Alright. Let's see. I'll look into this for another... Whoops. Probably another, like, 15 minutes or so. I might cut out early tonight. Like, if I'm going to have to look up stuff later or talk to people, then it doesn't make so much sense to just waste time doing it here. The resistors between is probably not necessarily a good method. Because depending on their charges, yeah, that could be a little weird. wonder if there's a comparator that can do this. This Texas Instruments paper is interesting. I'm surprised there's not a balancing controller that will just do this. Let's see. Controller IC. Maybe this is a thing. There is a Texas Instruments chip that does this. The BQ, I don't know if it's usable though. What is it? 77PL900. Doesn't look easy to use. Oh, wow. Yeah, they're basically this pretty complex part. I don't need anything that crazy. This stuff is, I think, designed for like EVs and things. Yeah, where you need to put a ton of cells in something so that you have a high voltage. Sheesh. This is incredible. I wonder if I could do all of this with one chip, right? Like if they weren't in series, if you'd had them split up, I wonder if this could do all of them. This is an awesome circuit they got going here. Oh, there's so much to this. I wish I knew what they used internal to like these little like 2-cell packs. Interesting. Okay. I may have found something. Here we go. Voltage protection with automatic cell balance for 2-cell lithium ions. Pretty straightforward schematic, just an annoying part to use because it's, yeah, package type. Power tools, battery backup systems. Automatic cell imbalance correction. And yeah, we need one of these for each of the series. Cell balance enable, active low, delay time. Duration, okay. This is closer. This is definitely closer. Okay. Ooh, excuse me. Cell balancing current is 10 milliamps. Interesting, okay. So this could work. I wish it came in an easier to use package. Like, not this, what is this even called? This VSON. But this does make me feel better. That it might be possible to do. So we just have to find the right thing. It's recommending protection. Like searching this in Google recommends protection ICs, which are nice. They are useful, but I don't know if this is exactly what I want. Yeah, it doesn't look like there's any balancing going on here. So this looks like the best option so far, and we'll use it if we have to, because I don't think we have any other choice. Worst case scenario, we just leave a lot of this stuff off and we just charge the batteries externally, which would be really sad, but if we gotta, we gotta. Another great alternative would be to find a 7.4 volt battery. No, I'm still not. I'm trying to. So I was thinking for a second maybe we could do some sort of circuit where when it's charging, it basically breaks them up into 8 separate batteries and charges them all separately. And then when you unplug the charger, it, the switches close and everything goes back to its normal system. But I don't see that. Yeah. There's some flaws with that system. One is like when they're discharging, they still aren't necessarily guaranteed to discharge evenly. So there's some options here. I need to go through and check this out. I think I'm going to take a break for now. I've read so much stuff, and this has been pretty boring. I'm going to see if I can figure it out. If anybody has any ideas, though, please send it to me, because that would be awesome. If someone could just give me or anyone that might know anything about this could give me an idea. That might work. That'd be cool. Let's see here. Just because it makes me feel better, I want to see the circuit boards so far. Give me a second. It's loading. Okay, so there's everything laid out. And it sounds like we're going to have some more chips to get this battery stuff to work. So, all right. Well, thank you for joining me tonight, those of you that did. And I will see you all later. Hopefully I can figure out a solution or come up with one to solve this problem with these batteries. Because I really, really want to use some sort of rechargeable system. But I think the simplest solution here is just to find a battery that is a 2-cell in series. And then I can connect them together like that. And then I could do something between them to keep them more or less even. But we need to still need to figure this part out. So, all right. Well, thank you all for joining me tonight. And I will see you later.